The NIM Programming Language. NIM Tutorial, Part Roman 2. Author, Andreas Rumpf. Version, 2.2.2. Basic types. This section deals with the basic built-in types, and the operations that are available for them in detail. Booleans. NIM's Boolean type is called bool, and consists of the two predefined values true and false. Conditions in while, if, elif, and when statements must be of type bool. The operators not, and, or, nor, less than, equals, greater than, equals, not equals, are defined for the bool type. The and or operators perform short-circuit evaluation. For example, while p not equals nil and p dot name not equals size. Hash p dot name is not evaluated if p equals nil. P equals p dot next. Characters. The character type is called char. Its size is always 1 byte, so it cannot represent most UTF-8 characters, but it can represent one of the bytes that makes up a multi-byte UTF-8 character. The reason for this is efficiency. For the overwhelming majority of use cases, the resulting programs will still handle UTF-8 properly, as UTF-8 was especially designed for this. Character literals are enclosed in single quotes. Chars can be compared with the equals, less than, equals, greater than equals operators. The dollar operator converts a char to a string. Chars cannot be mixed with integers. To get the ordinal value of a char, use the ord proc. Converting from an integer to a char is done with the chr proc. Strings. String variables are mutable, so appending to a string is possible, and quite efficient. Strings in NIM are both zero-terminated, and have a length field. A string's length can be retrieved with the built-in len procedure. The length never counts the terminating zero. Accessing the terminating zero is an error. It only exists so that a NIM string can be converted to a C string without doing a copy. The assignment operator for strings copies the string. You can use the AND operator to concatenate strings, and add to append to a string. Strings are compared using their lexicographical order. All the comparison operators are supported. By convention, all strings are UTF-8 encoded, but this is not enforced. For example, when reading strings from binary files, they are merely a sequence of bytes. The index operation SI means the ith char of S, not the ith unichar. A string variable is initialized with the empty string. Integers. NIM has these integer types built in. Int 8 1632 64 uint 8 1632 64. The default integer type is int. Integer literals can have a type suffix to specify a non-default integer type. Let x equals 0 hash x is of type int. Y equals 0 8 hash y is of type int 8. Z equals 0 32 hash z is of type int 32. U equals 0 u hash u is of type uint. Most often integers are used for counting objects that reside in memory, so int has the same size as a pointer. The common operators plus minus asterisk div mod less than equals not equals, greater than equals are defined for integers. The and or nor not operators are also defined for integers, and provide bitwise operations. Left bit shifting is done with the SHL, right shifting with the SHR operator. Bit shifting operators always treat their arguments as unsigned. For arithmetic bit shifts, ordinary multiplication or division can be used. Unsigned operations all wrap around. They cannot lead to over or underflow errors. Lossless automatic type conversion is performed in expressions where different kinds of integer types are used. However, if the type conversion would cause loss of information, the range defect is raised if the error cannot be detected at compile time. Floats. NIM has these floating point types built in. Float 3264. The default float type is float. In the current implementation, float is always 64 bits. Float literals can have a type suffix to specify a non-default float type. Var x equals 0.0 hash x is of type float. Y equals 0.032 hash y is of type float 32. Z equals 0.064 hash z is of type float 64. The common operators plus minus asterisk slash, less than equals, not equals, greater than equals are defined for floats, and follow the IEEE 754 standard. Automatic type conversion in expressions with different kinds of floating point types is performed. The smaller type is converted to the larger. Integer types are not converted to floating point types automatically, nor vice versa. Use the to int and to float procs for these conversions. Type conversion. Conversion between numerical types is performed by using the type as a function. Var x int 32 equals 1. Int 32 hash same as calling int 32 1. Y int 8 equals int 8 hash equals 978. Z float equals 2.5 hash int 2.5 rounds down to 2. Sum int equals int x plus int y plus int z hash sum equals 100. Internal type representation. As mentioned earlier, the built-in $stringify operator turns any basic type into a string, which you can then print to the console using the echo proc. However, advanced types, and your own custom types, won't work with the $operator until you define it for them. Sometimes you just want to debug the current value of a complex type without having to write its $operator. You can use then the reproc, which works with any type, and even complex data graphs with cycles. The following example shows that even for basic types there is a difference between the $and repr outputs. Var my bool equals true. My character equals n. My string equals nim. My integer equals 42. My float equals 3.14. Echo my bool, repr my bool. Hash, true true. Echo my character, repr my character. Hash, n. Echo my string, repr my string. Hash, nim 0x10 far 8c050, nim. Echo my integer, repr my integer. Hash, 4242. Echo my float, repr my float. Hash, 3.14 3.14. Advanced types. In nim, new types can be defined within a type statement. Type biggest int equals int 64 hash biggest integer type that is available. Biggest float equals float 64 hash biggest float type that is available. Enumeration and object types may only be defined within a type statement. Enumerations. A variable of an enumeration type can only be assigned one of the enumeration's specified values. These values are a set of ordered symbols. Each symbol is mapped to an integer value internally. The first symbol is represented at runtime by 0, the second by 1, and so on. For example, type direction equals enum north, east, south, west. Var x equals south hash x is of type direction, its value is south. Echo x hash prints south. If x equals direction dot south. Echo it's south. All the comparison operators can be used with enumeration types. An enumeration's symbol can be qualified to avoid ambiguities. Direction dot south. The $operator can convert any enumeration value to its name, and the odd proc can convert it to its underlying integer value. For better interfacing to other programming languages, the symbols of enum types can be assigned an explicit ordinal value. However, the ordinal values must be in ascending order. Ordinal types. Enumerations, integer types, char and bool, and subranges are called ordinal types. Ordinal types have quite a few special operations. Ord x returns the integer value that is used to represent x's value. Inc x increments x by 1. Inc x n increments x by n. N is an integer. Dec x decrements x by 1. Dec x n decrements x by n. N is an integer. Suc x returns the successor of x. Suc x n returns the nth successor of x. Pred x returns the predecessor of x. Pred x n returns the nth predecessor of x. The inc, dec, suc and pred operations can fail by raising an range defect or overflow defect. If the code has been compiled with the proper runtime checks turned on. Subranges. A subrange type is a range of values from an integer or enumeration type, the base type. Example. Type my subrange equals range 0.5. My subrange is a subrange of int, which can only hold the values 0 to 5. Assigning any other value to a variable of type my subrange is a compile time or runtime error. Assignments from the base type to one of its subrange types, and vice versa, are allowed. The system module defines the important natural type as range 0.high int. High returns the maximal value. Other programming languages may suggest the use of unsigned integers for natural numbers. This is often unwise. You don't want unsigned arithmetic, which wraps around just because the numbers cannot be negative. NIM's natural type helps to avoid this common programming error. Sets. The set type models the mathematical notion of a set. The set space type can only be an ordinal type of a certain size, namely int 8 int 16, uint 8 / byte uint 16, char. In ordinal subrange types, i.e. range -10.10, or equivalent. When constructing a set with signed integer literals, the set space type is defined to be in the range 0. Default set elements -1, where default set elements is currently always 2 to 8. The maximum range length for the base type of a set is max set elements, which is currently always 2 to 16. Types with a bigger range length are coerced into the range 0. Max set elements -1. The reason is that sets are implemented as high-performance bit vectors. Attempting to declare a set with a larger type will result in an error. var s set int 64 hash error. Set is too large. Use std/sets for ordinal types with more than 2 to 16 elements. Note: NIM also offers hash sets, which you need to import with import std/sets, which have no such restrictions. Sets can be constructed via the set constructor. Curly braces is the empty set. The empty set is type compatible with any concrete set type. The constructor can also be used to include elements and ranges of elements. Type char set equals set char. var x char set x equals z 0.9 hash. This constructs a set that contains the letters from to z and the digits from 0 to 9. The module std/setutils provides a way to initialize a set from an iterable. Import std/setutils. Let unique chars equals myString.toSet. These operations are supported by sets. A plus B, union of two sets. A asterisk B, intersection of two sets. A minus B, difference of two sets, A without B's elements. A equals B, set equality. A less than equals B, subset relation, A is subset of B or equal to B. A less than B, strict subset relation, A is a proper subset of B. E in A, set membership, A contains element E. E not in A does not contain element E. Contains A contains element E. Card A, the cardinality of A, number of elements in A. Incl A, elim, same as A equals A plus elim. Excl A, elim, same as A equals A minus elim. Bit fields. Sets are often used to define a type for the flags of a procedure. This is a cleaner and type-safe solution than defining integer constants that have to be ORed together. In sets and casting can be used together as in type myFlag asterisk dot size of sint equals in abcd. myFlags equals set myFlag. Proctor f myFlags int equals cast sint f. Proctor flags v int myFlags equals cast myFlags v. Assert to equals 0. Assert to equals 1. Assert to d equals 8. Assert to a c equals 5. Assert to flags 0 equals. Assert to flags 7 equals a b c. Note how the set turns in values into powers of 2. If using enums and sets with c, use distinct sint. For interoperability with C, see also the bit size pragma. Arrays. An array is a simple fixed-length container. Each element in an array has the same type. The array's index type can be any ordinal type. Arrays can be constructed using brackets. Type int array equals array 0.5 int hash an array that is indexed with 0.5. var x int array x equals 1, 2, 3, 4, 5, 6. For I in low x high x. Echo x I. The notation x I is used to access the ith element of x. Array access is always bounds checked at compile time or at runtime. These checks can be disabled via pragmas or invoking the compiler with the bound checks (off command line switch. Arrays are value types, like any other NIM type. The assignment operator copies the whole array contents. The built-in len prop returns the array's length. The low returns the lowest valid index for the array and high the highest valid index. Type direction equals in north, east, south, west. Blink lights equals in off, on, slow blink, medium blink, fast blink. Level setting equals array north west, blink lights. var level setting. Level north equals on. Level south equals slow blink. level east equals fast link. Echo level hash on, fast link, slow link, off. Echo low level hash north. Echo len level hash 4. Echo high level hash west. The syntax for nested arrays, multidimensional, in other languages is a matter of appending more brackets, because usually each dimension is restricted to the same index type as the others. In Nim you can have different dimensions with different index types, so the nesting syntax is slightly different. Building on the previous example, where a level is defined as an array of enums indexed by yet another enum, we can add the following lines to add a light tower type subdivided into height levels accessed through their integer index. Type light tower equals array 1.10, level setting. Var tower, light tower. Tower 1 north equals slow blink. Tower 1 east equals medium blink. Echo len tower hash 10. Echo len tower 1 hash 4. Echo tower hash slow blink, medium blink, more output. Hash the following lines don't compile due to type mismatch errors. Hash tower north east equals on. Hash tower 0 1 equals on. Note how the built-in len prop returns only the array's first dimension length. Another way of defining the light tower to better illustrate its nested nature would be to omit the previous definition of the level setting type, and instead write it embedded directly as the type of the first dimension. Type light tower equals array 1.10, array north.west, blink lights. It is quite common to have arrays start at 0, so there's a shortcut syntax to specify a range from 0 to the specified index -1. Type int array equals array 0.5, int hash an array that is indexed with 0.5. Quick array equals array 6, int hash an array that is indexed with 0.5. Var x, int array. Y, quick array. X equals 1 2 3 4 5 6. Y equals x. For I in low x high x. Echo x I y I. Sequences. Sequences are similar to arrays, but of dynamic length, which may change during runtime, like strings. Since sequences are resizable, they are always allocated on the heap, and garbage collected. Sequences are always indexed with an int starting at position 0. The len, low and high operations are available for sequences too. The notation x, I, can be used to access the ith element of x. Sequences can be constructed by the array constructor brackets in conjunction with the array to sequence operator at. Another way to allocate space for a sequence is to call the built-in newSec procedure. A sequence may be passed to an open array parameter. Example. Var x, sec, int, hash a reference to a sequence of integers. X equals at 1 2 3 4 5 6, hash the at turns the array into a sequence allocated on the heap. Sequence variables are initialized with at brackets. The for statement can be used with one or two variables when used with a sequence. When you use the one variable form, the variable will hold the value provided by the sequence. The for statement is looping over the results from the items iterator from the system module. But if you use the two variable form, the first variable will hold the index position, and the second variable will hold the value. Here the for statement is looping over the results from the pairs iterator from the system module. Examples. For value in at 345, echo value 345. For I, value in at 345, echo index $I, value $value. Index 0, value :3. Index 1, value :4. Index 2, value :5. Open arrays. Note, open arrays can only be used for parameters. Often fixed size arrays turn out to be too inflexible. Procedures should be able to deal with arrays of different sizes. The open array type allows this. Open arrays are always indexed with an int starting at position 0. The len, low and high operations are available for open arrays too. Any array with a compatible base type can be passed to an open array parameter, the index type does not matter. Var fruits. Sec, string, hash reference to a sequence of strings that is initialized with, at brackets. Capitals. Array, 3, string, hash array of strings with a fixed size. Capitals equals, New York, London, Berlin, hash array, capitals, allows assignment of only 3 elements. Fruits not add, banana, hash sequence, fruits, is dynamically expandable during runtime. Fruits not add, mango. Proc open array size, open array, string, int equals len. Assert open array size, fruits, equals, 2 hash procedure accepts a sequence as parameter. Assert open array size, capitals, equals 3 hash, but also an array type. The open array type cannot be nested. Multidimensional open arrays are not supported because this is seldom needed and cannot be done efficiently. Varargs. A varargs parameter is like an open array parameter. However, it is also a means to implement passing a variable number of arguments to a procedure. The compiler converts the list of arguments to an array automatically. Proc my right line F, file, A, varargs, string, equals. For S in items A. Right F, S. Right F, \n. My right line, stdout, abc, def, size. Hash is transformed by the compiler to my right line, stdout, abc, def, size. This transformation is only done if the varargs parameter is the last parameter in the procedure header. It is also possible to perform type conversions in this context. Proc my right line, F, file, A, varargs, string, $, For S in items A. Right F, S. Right F, \n. My right line, stdout, 123, abc, 4.0. Hash is transformed by the compiler to my right line, stdout, 123, abc, 4.0. In this example, $is applied to any argument that is passed to the parameter A. Note that $applied to strings is a no-op. Slices. Slices look similar to subranges types in syntax, but are used in a different context. A slice is just an object of type slice, which contains two bounds A and B. By itself a slice is not very useful, but other collection types define operators, which accept slice objects to define ranges. Var A equals, nim is a programming language. B equals, slices are useless. Echo A, 7.12, hash, a prog. B, 11.2 equals, useful. Echo B hash, slices are useful. In the previous example, slices are used to modify a part of a string. The slices bounds can hold any value supported by their type, but it is the proc using the slice object which defines what values are accepted. To understand the different ways of specifying the indices of strings, arrays, sequences, etc., it must be remembered that nim uses zero-based indices. So the string B is of length 19, and two different ways of specifying the indices are. Slices are useless. 0, 11, 17 using indices. 19, 8, 2 using syntax. Where B, 0.1 is equivalent to B, 0.b.len minus 1, and B, 0.less than B.len, and it can be seen that the 1 provides a shorthand way of specifying the B.len minus 1. See the backwards index operator. In the above example, because the string ends in a period, to get the portion of the string that is useless and replace it with useful. B 11.2 is the portion useless, and B 11.2 equals useful replaces the useless portion with useful, giving the result slices are useful. Note 1. Alternate ways of writing this are B 8.2 equals useful, or as B 11.b.len minus 2 equals useful, or as B 11.less than b.len minus 1 equals useful. Note 2. As the template returns a distinct int of type backwards index, we can have a last index constant defined as const last index equals 1, and later used as b 0. Last index. Objects. The default type to pack different values together in a single structure with a name is the object type. An object is a value type, which means that when an object is assigned to a new variable, all its components are copied as well. Each object type foo has a constructor foo field value, where all of its fields can be initialized. Unspecified fields will get their default value. Type person equals object. Name, string. Age, int. Var person 1 equals person, name. Peter, age, 30. Echo person 1.name hash, Peter. Echo person 1.age hash 30. Var person 2 equals person 1 hash copy of person 1. Person 2.age plus equals 14. Echo person 1.age hash 30. Echo person 2.age hash 44. Hash the order may be changed. Let person 3 equals person, age, 12, name, Quentin. Hash not every member needs to be specified. Let person 4 equals person, age, 3. Hash unspecified members will be initialized with their default values. In this case it is the empty string. Do assert person for .name equals. Object fields that should be visible from outside the defining module have to be marked with asterisk. Type. Person asterisk equals object hash the type is visible from other modules. Name asterisk. String hash the field of this type is visible from other modules. Age asterisk. Int. Tuples. Tuples are very much like what you have seen so far from objects. They are value types, where the assignment operator copies each component. Unlike object types though, tuple types are structurally typed, meaning different tuple types are equivalent if they specify fields of the same type and of the same name in the same order. The tuple constructor parenthesis can be used to construct tuples. The order of the fields in the constructor must match the order in the tuple's definition. But unlike objects, a name for the tuple type may not be used here. Like the object type, the notation t.field is used to access a tuple's field. Another notation that is not available for objects is ti to access the ith field. Here I must be a constant integer. Type. Hash type representing a person. Hash a person consists of a name and an age. Person equals tuple. Name, string. Age, int. Hash alternative syntax for an equivalent type. Person x equals tuple, name, string, age, int. Hash anonymous field syntax. Person y equals string, int. var person, person. Person x, person x. Person y, person y. Person equals name, Peter, age, 30. Hash person and person x are equivalent. Person x equals person. Hash create a tuple with anonymous fields. Person y equals Peter, 30. Hash a tuple with anonymous fields is compatible with a tuple that has field names. Person equals person y. Person y equals person. Hash usually used for short tuple initialization syntax. Person equals Peter, 30. Echo person dot name hash Peter. Echo person dot age hash 30. Echo person 0 hash Peter. Echo person 1 hash 30. Hash you don't need to declare tuples in a separate type section. var building. Tuple, street, string, number, int. Building equals Rudel Perseb, 13. Echo building dot street. Hash the following line does not compile, they are different tuples. Hash person equals building. Hash, error. Type mismatch. Dot, tuple, street, string, number, int but expected, person. Even though you don't need to declare a type for a tuple to use it, tuples created with different field names will be considered different objects, despite having the same field types. Tuples can be unpacked during variable assignment. This can be handy to assign directly the fields of the tuples to individually named variables. An example of this is the split file proc from the OS module, which returns the directory, name, and extension of a path at the same time. For tuple unpacking to work, you must use parentheses around the values you want to assign the unpacking to, otherwise, you will be assigning the same value to all the individual variables. For example, import std/os. Let path equals user/local/nimp.html. Dir name ext equals split file path. Badir bad name madext equals split file path. Echo dir hash outputs user/local. Echo name hash outputs nimp. Echo ext hash outputs .html. Hash all the following output the same line. Hash dir user/local name nimp ext .html. Echo badir. Echo bad name. Echo madext. Tuple unpacking is also supported in for loops. Letter equals 10 20 b 30 c. For x c in a. Echo x. Hash this will output 10 20 30. Hash accessing the index is also possible. For I x c in a. Echo I c. Hash this will output 0a 1b 2c. Fields of tuples are always public, they don't need to be explicitly marked to be exported, unlike for example fields in an object type. Reference and pointer types. References, similar to pointers in other programming languages, are a way to introduce many-to-one relationships. This means different references can point to and modify the same location in memory. NIM distinguishes between traced and untraced references. Untraced references are also called pointers. Traced references point to objects in a garbage collected heap. Untraced references point to manually allocated objects or objects elsewhere in memory. Thus, untraced references are unsafe. However, for certain low-level operations, for example accessing the hardware, untraced references are necessary. Traced references are declared with the ref keyword. Untraced references are declared with the ptr keyword. The empty brackets subscript notation can be used to refer a reference, meaning to retrieve the item the reference points to. The dot, access a tuple / object field operator, and brackets, array / string / sequence index operator. Operators perform implicit dereferencing operations for reference types. Type node equals ref object. Ri, node. Data, int. var n equals node data, 9. Echo n dot data. Hash no need to write n brackets dot data. In fact n brackets dot data is highly discouraged. To allocate a new traced object, the built-in procedure new can be used. Var n, node. New, n. To deal with untraced memory, the procedures alloc, dealloc and realloc can be used. The system modules documentation contains further details. If a reference points to nothing, it has the value nil. Procedural type. A procedural type is a, somewhat abstract, pointer to a procedure. Nil is an allowed value for a variable of a procedural type. NIM uses procedural types to achieve functional programming techniques. Example. Proc greet, name, string equals, hello, and name and. Proc by, name, string equals, goodbye, and name and. Proc communicate, greeting, proc x, string, name, string, equals echo greeting, name. Communicate, greet, John. Communicate by, Mary. A subtle issue with procedural types is that the calling convention of the procedure influences the type compatibility. Procedural types are only compatible if they have the same calling convention. The different calling conventions are listed in the manual. Distinct type. A distinct type allows for the creation of a new type that does not imply a subtype relationship between it and its space type. You must explicitly define all behavior for the distinct type. To help with this, both the distinct type and its space type can cast from one type to the other. Examples are provided in the manual. Modules. NIM supports splitting a program into pieces with a module concept. Each module is in its own file. Modules enable information hiding and separate compilation. A module may gain access to the symbols of another module by using the import statement. Only top-level symbols that are marked with an asterisk are exported. Hash module A. Var x asterisk, y, int. Proc asterisk, a, b, sec int equals. Hash allocate a new sequence. New sec, result, len, a. Hash multiply two int sequences. For I in 0 dot less than len, a, result, I, equals a, I, asterisk b, I. When is main module? Hash test the new asterisk, operator for sequences. Assert at 123 asterisk at 123 equals at 149. The above module exports x and asterisk, but not y. A module's top-level statements are executed at the start of the program. This can be used to initialize complex data structures, for example. Each module has a special magic constant is main module that is true if the module is compiled as the main file. This is very useful to embed tests within the module as shown by the above example. A symbol of a module can be qualified with the module.symbol syntax. And if a symbol is ambiguous, it must be qualified. A symbol is ambiguous if it is defined in two or more different modules, and both modules are imported by a third one. Hash module A. Var x asterisk, string. Hash module B. Var x asterisk, int. Hash module C. Import A, B. Write st out, x, hash error, x is ambiguous. Write st out, ax, hash ok, qualifier used. Var x equals 4. Write st out, x, hash not ambiguous, uses the module C's x. But this rule does not apply to procedures or iterators. Here the overloading rules apply. Hash module A. Proc x asterisk a, int, string equals $a. Hash module B. Proc x asterisk a, string equals $a. Hash module C. Import A, B. Write st out, x, 3, hash no error, ax is called. Write st out, x, hash no error, bx is called. Proc x asterisk a, int, string equals discard. Write st out, x, 3, hash ambiguous, which x is to call. Excluding symbols. The normal import statement will bring in all exported symbols. These can be limited by naming symbols that should be excluded using the except qualifier. Import mymodule except y from statement. We have already seen the simple import statement that just imports all exported symbols. An alternative that only imports listed symbols is the from import statement. From mymodule import x, y, z. The from statement can also force namespace qualification on symbols, thereby making symbols available, but needing to be qualified in order to be used. From mymodule import x, y, z. X, use x without any qualification. From mymodule import nil. Mymodule.x, must qualify x with the module name as prefix. X, using x here without qualification is a compile error. Since module names are generally long to be descriptive, you can also define a shorter alias to use when qualifying symbols. From mymodule as m import nil. mx, m is aliasing mymodule. Include statement. The include statement does something fundamentally different than importing a module. It merely includes the contents of a file. The include statement is useful to split up a large module into several files. Include file A, file B, file C. Next. Part 2. So, now that we are done with the basics, let's see what NIM offers apart from a nice syntax for procedural programming. Part Roman 2.